given that your reports for your research projects are due relatively soon, I thought it'd be good for us to start reading more mixed methods papers to give you a flavor for what different designs are for mixing methods. And then we have a few papers that focus more on the methodological aspects of this interrupted time series analysis. And one in particular, the one that I think nobody signed up to present, shows, I think, a very, very powerful, even more so than the one we talked about, design, where you could do something very similar to what we saw together in class last time, but with an additional control time series. It gives you, I think, a much better sense of causality, even than the thing we discussed together. So that's the plan for today. Right. So I want to start with this one just because it, I think, showcases an application of the interrupted time series analysis as discussed in class exactly. So I thought it would be a good starting point. And
so before you put that up, you might have to.
No, not at all. The floor is yours.
I actually sent you a Slack message.
Oh,
I have a small demo.
yeah.
I sent you.
Love it. Cool. You have a demo.
Yeah, it's very tiny, but.
Want to make this? Want to make this bigger, or want me to knit it, or what?
This is good. I'm gonna go to the slideshow first.
Okay.
Run it? Is that what it is? Basically run all.
Yeah, I'm knitting it.
Okay.
Let's see. Wait. This?
Oh, I didn't know we could do that. That's great.
Is this it?
Yeah. That's it.
Okay, so you have it here, and you have your slide deck here. So
Cool.
I trust that you can navigate your.
Okay, I can do that. All right. Hello, everyone. I am going to present on adding sparkle to social changes. Let's see. Coding. Couldn't read that. It's a social coding, an empirical study of repository badges in the NPM ecosystem. And of course, Bogdan is one of the authors on here, which is good because I am going to describe what I think they did for the quantitative study to the best of my knowledge, including the small demo. And you can tell me that if I have it wrong. I think I have it right, but we'll see. All right. All right, so basically the study in a nutshell is, do GitHub badges provide good signals? So if anyone hasn't seen GitHub badges before, they look kind of like this. Basically, they give you an indication of your GitHub project about certain stats. So what does the test coverage look like for your project? Are your dependencies up to date? And they're displayed in the README, so you can get a very quick idea about some of the quick stats in your project. These badges are signals. So I don't know if you guys remember, I'm pretty sure we went over about signal theory in this class at some point, and it talked about how certain information provides people with signals. And I'm not going to go into detail about signal theory, but one of the important distinctions is there's surface level signals. They're very cheap to produce. They don't necessarily tell you anything interesting about your project. But there's also something called assessment signals, which are tougher to produce. And because they're tougher to produce, they might tell you something more meaningful about your project. So a good example of that might be like test coverage. If you have to set up a badge for test coverage, that's not easy. You might get a good idea about the test coverage for your project. So I also have some other examples. So basically, when we say that a badge is a signal, we want to know one example is a project more likely to write tests if they display a quality assurance badge? So what we're basically saying is because they display the quality assurance badge, do they actually write better tests? Another example is if a project is a project more likely to keep its dependencies up to date if it displays a dependency monitoring badge. So basically, that's what the authors are investigating. And this study is for NPM packages in particular. Yeah.
Just an aside on signaling theory, maybe one good example to illustrate this distinction between conventional signals, the cheap ones you refer to, and assessment signals, the more trustworthy, relatively expensive ones. It's something like signals of expertise. So on the one hand, you could self-proclaim on your Twitter or something that you're an expert in this or that. And that's very easy to fake, right? Because anyone can claim anything online, right? The standard of there's no credential required to prove that, right? You can self-claim anything, really. So that would be a conventional signal because it's relatively easy to produce and therefore relatively easy to fake. An example of maybe a assessment signal would be having a degree from CMU or something like that, because it's relatively expensive to produce, to obtain, not so much in terms of money, although that's true, but also in terms of effort, like to take hard courses and all that, do well in graduating get a degree, and it's harder to fake, right? So therefore, you can put some trust into having a degree from a place like CMU, and that's considered to be an assessment signal. Harder to obtain, therefore harder to fake, therefore more trustworthy. That's sort of the distinction here.
Cool.
Are these examples of research questions surrounding signal theory, or are they examples of what this study tried to find about signal theory?
It's more examples of what the study tried to find.
Okay.
It's right, investigating, for example, do quality assurance badges actually show what we think they intend to show?
Okay.
Yeah. Cool. All right. So there's two broad research questions in this paper. The first one is, what are the most common badges and what does displaying them intend to signal? So this is a qualitative research question. The authors did this with the survey, and I'm not going to focus on this question today. I will touch on it briefly in the next slide, though. The main research question I'm going to talk about today is the second one, which is to what degree do badges correlate with qualities that developers expect? So this is a quantitative study, and this is what I'm going to focus on today. All right. And also I should say, this is essentially asking to what degree are badges good signals? That's essentially what it's saying. All right, so for the qualitative study, which I'll mention very briefly. So Bogdan mentioned this is a mixed method paper, mixed method study. And so for the qualitative part, they looked at a whole bunch of different badges. And one of the things that they found were different types of badges, popularity badges, information badges, dependency management badges. And they take a look at them in all these different types in the paper. But I'm only going to focus on dependency management badges. So just one small part of the study I'm going to focus on. And there's a hypothesis for the dependency management badges, and it's that the adoption of dependency management badges correlate with fresher dependencies. So you get the different categories from the qualitative part of the study, and then we're going to try to falsify or show the hypothesis stands with the quantitative study. Okay. Make sense? And freshness here is a quantitative measure. What exactly it is not super important. All right. So do dependency management badges correlate with freshness? To do this, there's 3 different analyses in the paper. They use correlation, this other one called additional information, but I'm not going to go into any details about these. What I'm going to focus on is the longitudinal analysis that they perform. So for the longitudinal analysis, basically what they're investigating is, does introducing a first badge into a project, which is called the intervention, does this have an observable effect on the package's quality? And intuitively, we think it would, right? And it kind of makes sense that if you add this badge, it might help others understand that, yes, we have this quality. And all right. So the authors use time series regression discontinuity design. So this is basically a time series that we, in the flavor that we talked about last Thursday. And so to give you a rough idea about what this looks like, they basically took 18 months of data. So 9 months, so you have this purple bar, which is the intervention. This is when the first badge was introduced. And then before that, you have 9 months of data. And then after that, you also have 9 months of data. And the idea is you want to perform this RDD, and you want to see what does the regression look like before and after. And the main point is you want to see how discontinuous the regression lines are at the intervention point. That's the high level idea. Okay, so now, yeah.
Does lower mean pressure?
Yes, lower means fresher. Yeah, good point. I forgot to say it. All right, so now I'm going to go to a demo. So the purpose of this demo is, thank you, is this reminded me a lot of exactly what we did on Thursday. We all participated in this this in-class exercise, so I figured maybe it would help everyone understand what's going on a little bit better if I use this exact example. All right, so just to remind everyone, we have this plot where the idea is we want to, in one model, come up with basically 2 different regression lines for part of the same model for this data that goes from 0 to 200, but clearly there's some sort of intervention at time 100. And so what we want to do is see the discontinuity, right? So it's kind of like what's in here. So there were 3 different ways we talked about for modeling this. I personally chose one where it's rather small, but it looks like, can you guys see this? Okay. Where I have this indicator variable before. So it's 0 from time slots 0 to 100, or really to 99, and then it's 1 from 100 to 200. So it indicates before the intervention or after. And then we have a model here, and the main point is you multiply time, which is x, times before. And it gets you something that looks like this. Okay, great. So this is why, but there is another way to model this that we talked about. And it'll look kind of like this. So in addition to time, we also had time after. So time after is all zeros between 1 to 100, but then you start counting up 1, 2, 3, 4, 5 from 100 and on. So basically keeps track of time starting at time 100. And then we have another variable called intervention. Intervention is just an indicator variable that is 0 from time 0 to 100, or 0 to 99, and then 1 from 100 to 200. So in other words, intervention is the same as before, exactly. The same as the before variable. Great, and so if we fit so the new model is now x plus x after plus intervention. And the main thing I want you to remember is we're adding intervention here. And if we run this model, you get exactly what we saw before. So looking at intervention here, you'll notice that we have this negative 45. Now here's the part where I'm pretty sure about, but maybe not positive. The distance here is 45. It looks like about 45. So I'm pretty sure what this intervention is showing is the distance right there. Cool? Makes sense? All right, so right here. Got Oh, not share, sorry. Slideshow. Okay, so let's look at their model. So freshness is equal to a bunch of things. But most important, we have this, has this badge, has the dependency management badge times after intervention. So after intervention is the same as X after in the previous example. And then you have the same intervention, I'm pretty sure is an indicator variable. And so what I want to draw your attention to is the summary here where we say intervention is negative 0.93. So basically, this is analogous to the distance being about 0.93. It's a little bit different though. It's not the same as the previous example in two ways. The first is that the data is logarithmic. So it's actually not 0.93, it's 2.5. And second, it's not additive, it's multiplicative. So really what this 2.5 is saying is not the discontinuity, the distance isn't 2.5, but it's saying that the any project that has this badge is 2.5 times as likely to have fresher dependencies. All right. So I'm finally done. The conclusion is that the adoption of dependency manager badges is associated with a longer lasting effect on freshness than other badges. All right.
What's the mechanism
What do you mean?
through which displaying the badge would result in fresher dependencies?
You're asking about the theory or in the model?
Theory.
Oh, that's a good question. Okay, so back to signal theory, probably. Basically, the badge is an assessment signal. There's some cost to displaying the badge. And so if you were displaying the badge, presumably you're doing a good enough job at dependency management where you decided, okay, let's also throw the badge up. I mean, so you're already doing a good enough job at dependency management if you decide to adopt the badge. That's one idea?
Yep.
Okay.
Yeah, I think one other is maybe, I agree with the first one. One possible other one is you're under more pressure, there's more visibility into you having stale dependencies that just reflects poorly on you. Imagine you have people over all the time at your place. You know, if you keep it messy, there's more incentive for you to tidy up if you have people over all the time because of the social cost of having a messy house that others will see.
Yeah, that's a good point. They also said that in the paper too. I forgot about that. Yeah.
You could argue similarly here.
Does the group of analyze GitHub repos, like, are they all the same popularity? Because like if it's a popular project that has a lot of maintainers, or if you have a group of repos that are like, that is true of all of them,
Mhm.
then I would think that the social pressure would likely like have newer dependencies, like without the tag.
The social pressure would have newer dependencies. What do you mean?
Like whether or not you have this, what is it called, a tag?
Badge.
Badge.
Yeah.
Like whether or not you have this badge, like, could it just be that if you analyzed a group of repos that are all like very popular, very used, very maintained, but a subset of them have badges while the rest of them do not have badges for recent dependencies, like, is it likely that they are more recent dependencies? Like, does it do an analysis on similar repos as well?
I guess I'll say two things. One thing is maybe I didn't make it clear, but the badge is about dependencies in general. It's basically one badge that tells you how fresh all your dependencies are. So it's not like different badges per dependency. I wasn't sure if that was a point of confusion,
I mean, like,
but
like, couldn't there be an alternate explanation? Like, does the badge truly mean that you are more likely to have fresher dependencies, or is it that more used repositories that are more maintained and have more users have fresher dependencies, and then those tend to have badges on them? I don't know if I'm
Well,
crazy. I don't know if I'm crazy at all, but
well, I feel like that if that were the case, that would still indicate that the badge is doing its job, no?
I'm more like asking if is it the badge that's doing it, or is it the social pressure of like the use of like how many people?
Oh, you're asking if the badge is causing it? Is that part of your question?
Yeah.
Oh, that's very interesting. I hadn't considered that. Well, what Bogdan said kind of indicates that it could be a cause, so I think totally, right? Like, well, no, I mean, it makes sense, right? Like, if you're trying to, you know, if you display this badge, you don't want to say like all dependencies are out of date, right? You have so in that case, I could see it causing that. Also, you made this, you mentioned about does it look at repositories that are similar in popularity? It looked at a bunch of different repositories. The only requirement was that okay. One of the requirements is that there were NPM packages. Other than that, the only filtering was done based on like data availability and stuff like that. So they weren't all just as popular. In fact, there were popularity badges. So they do talk about different projects with different popularities.
Yeah, because I'm more like, is there, if they're taking a bunch of repositories where they are at different popularities, and then the ones that are the most popular tend to have the most up-to-date dependencies, but then a subset of those have badges on them, then couldn't you argue that like the most popular ones due to social pressure have the most up-to-date dependencies, and then the badges are just kind of like superfluous?
I think okay, so you're almost saying like is it not a cause?
Like, is the analysis tainted by the non-popular repositories also being removed?
I think what you're saying, okay, I think I finally understand what you're saying. I think it matters for the explanation of whether there's a causal relationship or not, but they don't draw any causal relationships in here. Mostly they're just concerned with whether badges are a signal, and I think what you're saying doesn't affect whether it's a signal. So I think you're making a good point, but the primary focus is whether badges are a signal, and I don't think that.
Okay, so it's just the research question.
Right, exactly. Did I get that right?
Sort of do. I'll tell you a bit about this. I thought you were going to pick up on something. In fact, you had it on your slide earlier, and it's the thing I ended class with last time. So the thing I told you about last time is that I am insisting on you modeling all of this in one single model, because why? Yeah. So actually, if you notice this regression summary of a single model, you notice that only 3 of the variables here are in fact the ones modeling the RDD part of this. Everything else, including star counts, are control variables. Okay, so really the claim is much stronger, I think, than you're implying, right? Because we're controlling for a number of things, you know, direct and reverse dependencies and star counts and a bunch of other things. And given all of those held constant, we're making this claim about the badge being present or not. So it really is, I think, a much stronger argument than you were suggesting earlier. Does that make sense?
I understand you're controlling for all these things, but it's stronger than I suggested.
Because the interpretation of this coefficient is while holding constant the number of stars and the number of direct and reverse dependencies and the number of whatever else. So given two packages that are otherwise similar on these dimensions, the one with the badge does this versus the one without the badge does not.
Right, okay, yeah, I see what you're saying.
So I think this directly answers the question you had earlier. There's another trick here, but maybe there was a question.
So if we were to be doing something similar, would we just make everything an independent variable in our model?
With a footnote. Everything footnote. What's the footnote?
Everything that we want to control. But like, do we want to control everything or?
Yes, everything that we have a reason to control for, we include in the model. Yes, correct.
One thing I was worried about is like, if you have too many variables, then you might overfit. Is that something that you have to think about in this case? Or
Not when you have, I don't know, tens of thousands of data points that you're regressing over. Yeah. Usually when we do this, there's just so much data that it doesn't matter. The other cool thing here that I wanted to draw your attention to is the following. And sort of, you mentioned this, but I want to highlight it. What you see here is distributions of this freshness metric over time, right? So every project being analyzed in this sample contributes 18 data points or something, 19 data points. Okay, and this is the distribution of the values of those freshness metric across this entire sample of however many tens of thousands of projects. And I think the horizontal line here is the median of this box line. That's sort of tells you kind of what the shape of this is. So now, the reason why this is interesting, or a reason why this is interesting, is because you will rightfully argue that probably each of the projects in the sample, the packages in the sample, adopted the badge being studied at a different time, right? This is something they can choose to do whenever. It's not like, GitHub comes and says, now we all have badges, let there be badges, right? People choose to do this, who knows when, and in fact, there's probably a huge span here, from the earliest adopter to the latest adopter in the sample. Okay, so what happens is, you take all of these individual packages that have adopted the badge, and you have this history before and after. You take all of these, and then you align them on this intervention date. Okay, because for the purpose of modeling the trends, here, it doesn't matter if it was in 2018 or 19 or 2020 or who knows when. Right? This is actually really good from a causal inference perspective, because it automatically removes a bunch of confounds here for free, just by design, which is always a good thing. Right? For example, what if, I don't know, GitHub introduced a new feature or had some policy or who knows what in 2015 that would have affected, the projects that adopted the badge around that time. But surely you won't be able to argue this for every single time point. Right? So by taking this, interventions that have happened at wildly varying times and studying them jointly, you're naturally controlling for external factors that may have coincided with some of these interventions. But certainly they couldn't have coincided with all of these interventions. That's very impossible. Right? So I mean, you're right, we're not making strong causal claims in the paper, But this is actually, it's pretty, it's pretty solid, I think, analysis that gives a lot of confidence. I'm still not making, of course, I'm not making causal claims even now, but I think the analysis is quite solid, right? Because of these two reasons. One is controlling for other things in the regression, and two is this sort of design that allows you to align on this intervention date, regardless of when they happen. Right? Because we don't have just one individual that experienced the intervention at some point, or a group of individuals that all experience the intervention at some point, which is what usually happens with something like policy interventions. With policy, the government comes and they, I don't know, smoking ban in Sicily or something, example we started from. The government comes, introduces the smoking ban, affects everyone at the same time. Okay? Here, that's absolutely not the case, and that's a good thing. Okay, so, in a setting like this, you have the luxury, right, of sort of, by design, controlling for some of these compounding factors, when you could do this sort of alignment at the intervention date. Which you don't get, for example, with something like policy. That would be nice. Okay, so these were two things here that I thought were touching. Thanks. Any thoughts, questions? Yes, does it make sense? Okay, very good. So I think we'll move on to Owen's. Great. Gonna do it? Awesome. Thanks. What was yours?
Okay, so I guess that's an interesting topic to us, but an interesting topic nonetheless in terms of segmented regression and interrupted time series. So they did this review of medical study where interrupted time series were used. So last week we looked at this. I don't think I would spend too much time on this. Disclaimer. I think Ian said 45, I had 47 here. Because I grouped 100 to the before intervention rather than the after intervention. Otherwise it's probably 45. Yeah, and below is the model, how we would write it out. And one thing we, I think, briefly maybe touched last week is the reason that we're stressing on the point that this is very effective is because you can measure the effectiveness of a certain intervention before the intervention takes place and after the intervention actually happens. So in the paper, they gave calculation. So in this case, let's say at time t equals 150, the effectiveness or whatever this science trying to model reduced by 82.47% because of the intervention at t equals 100. So, well, I guess this probably most of us would understand that you can have one intervention, you can have multiple interventions, and all of the coefficients could be modeled, and no matter how many interventions happen, you would just have a very complicated model with many coefficients. And here's the numbers you will plug in. So one interesting thing that we didn't cover is something called lag effects. So let's say, so let's say some ineffective drug was taken off the market at this point, which is something like month 17 or something. And we see that this bottom line, which is the number of ineffective drugs sold, goes to zero immediately because it was taken off the market. We see that the substitute actually remained in the range of the model before the intervention for a couple of months before it shot up, and then the later model is probably different than before the intervention. So the author suggests that there's two ways to approach to deal with this lag effect. One is you can just take it out. You can just compare the model before intervention and after where the lag effect ends. Presumably you will see it from the data points that you collect. The other way is if you have a long enough period of data collected during the lag effect, you can model this separately. So you will essentially have 3 different segments, but like we said, put into one linear regression model. I might need to refresh this because I did make some slight changes. Maybe I'll refresh. Nice. The other thing is called wild data points. So 1981, New Hampshire introduced this cap of 3 prescription drugs per medicated user patient. And we see that before the 3 drug cap begins, the number of prescription drugs per patient shot up. Like this data point is clearly not within this model. So this could happen. We might have a reasonable guess that people know this cap is going to be introduced, so they ask for more prescribed drugs or something like that. So the author suggests if you have a reasonable explanation, you can leave this point in this model, but you just take notes of what happened here. But most cases, you probably don't understand. Well, if you don't understand what happened here, you just take it out and you model this as before, and this is after. And taking this out is somewhat important because with this data point, just one data point, your model will presumably like have an increased slope, and this slope could have a bigger effect if we measure it over time. So let's say if we want to compare how effective this 3 drug cap is over like 1 or 2 years later, then the gap here, the percentage I showed before, might be bigger. Well, will definitely be bigger if you have this wild data points layering around. Okay, last thing, still on this Medicaid cap of 3 drugs, we see that the dark line, it might be harder to see, but this top line is New Hampshire, and the bottom line is another state. So, and the y-axis is the percent of people in nursing home, or percent of participants in the nursing homes. And one note is I actually needed to look into the original paper to figure that out, but nursing homes have no cap in prescription drugs. So, but the point of this is, in real world, you might not know like how to model this. You know where the intervention happened, but you don't know like how effective are the interventions at the time of it happening. So New Jersey is introduced here because they don't have a cap and they're used here as a control group. And if we look at the slope, this is hand drawn for reference only. We see that this when after the 3 drug cap was implemented, the red the slope of the after intervention, which is illustrated by the red line here, is higher than the blue line at the bottom when compared to the control group, because nursing homes have no caps on prescription drugs, or they have alternative explanations, such as people have bigger issues when they can't get enough prescription drugs and they have to go into nursing homes or something like that. But this just shows you that sometimes looking at one set of data is not enough, and you will need to introduce a control group to see how effective certain interventions are. And this is I guess, reverse intervention where the cap is actually replaced by a $1 copay, and we see that the slope after goes more closely to the control group. There are other things that I didn't take out time to cover during class, but the paper pointed out other ways to control for error, and also different approaches of controlling different ways of introducing a control group to measure the effectiveness of intervention groups. Are there any questions, comments?
Could you show us, this was great, thank you very much. Could you show us please the model for this multiple intervention design? How exactly they specify that? You had it, I think, a couple of slides ago.
This one?
Yeah, maybe here.
Oh, yeah.
Right.
Sure. So we have up to this line, and well, this is not from the paper, this, well, this is from the paper, but this model is a continuation of what we had last week. So we'll introduce, just like last time, when we introduced intervention one, the variable, which is 0 before 100 and 1 after 100. Now it is 1, it's still 1 after 100 because that intervention, let's assume, didn't get canceled or something, it's still there. So we know beta 3, so we'll introduce another variable intervention 2, which is 0 before 200 and 1 after 200. And this time after second intervention, also the same as time after first intervention, it's 0 before 200 and it started counting after the 200 time. So yeah, and I guess last time we did some mathematical deductions to conclude that the slope of this line is indeed beta 1 plus beta 3, not just beta 3, because well, I can't hard to explain, but it's indeed this plus this. And the slope after the second intervention will be the 3 coefficients added together of the first, second, and third outputs from the R or from the regression model.
Yeah.
So what if we have some information that is cancelled? For example, say an haircut, you do the information haircut, and if you do a different haircut, the second information will be.
In terms of y-axis differences?
And the parameters that we'll have. So the iteration flag will be 0 after 200.
Say that again.
So in this case, the first integration will continue after the second integration starts.
Yes.
But in some cases, if of course that it's a substitution. So for example, if you get an haircut on the first integration and you get the second haircut on the second integration, then you'll have 2 interventions that will not be in place after the second one.
Right.
So how would that impact the parameters that we have?
Yep. All it one.
My understanding is if intervention 2 is a replacement of intervention 1, then the number here should be 0 after 200.
That makes sense.
I don't know the effect it will have on beta 5 because presumably if you change that number, the model will be different because this is actually the data points you collect. But I believe the coefficient here will stay the same because of the slope, but the changing level will probably be different in terms of the output from R and the actual difference you see here. I'm not 100% sure.
I think I agree with this. I think the change in level would be relative to no intervention at all before, rather than to the first haircut, which is the current design. Just the interpretation of the coefficient changes, but I don't see a problem at all.
So the coefficients will be the same because we still have three parts of the model. The interpretation of those coefficients will be different.
And the value will be different here. I think beta 4 will have a different value in that case.
Right. Yeah, it depends on what we are not, yes. But yeah, the interpretation will be always compared to this time before.
To what was before, yes, where you were before.
Thank you.
Awesome, thank you. Leave it on for a second. One more thing I want to mention, but thanks so much. This was great. Yeah, good job.
Thank you.
The thing you mentioned here, to make sure we're all on the same page. What we did in the paper we read before is to lazily throw away all the data around the time of the intervention. Because we said, look, it's unstable, there's lots of changes that are happening when they introduce those badges. And there's other things in flux, so we don't want to bother with this extra noise. And we're looking at it over long periods of time anyway, so that whatever extra noise and variation there is right there, we don't really care about. So we just threw it away. You mentioned also this as one solution, just throw away. In this case, there was maybe a rollout period during which the intervention was being gradually introduced or something, which is analogous to the setting we had, where there was maybe other stuff happening at the same time. So you could throw it away. You mentioned this here as well, or you could do exactly what you showed us before. If you want to be like extra rigorous, you could do this. You could say, this is when the intervention started being rolled out, and there's some transition period, and this is when it was fully rolled out. And then you can model those in separate segments. So it's totally fine as well. Okay, great. So now let's look a little bit at this paper. This was really excellent paper. I highly recommend that you look at this if you haven't read it already. It's also very short, just has, I don't know, has 10 pages if you count the appendices and the references and so on. So it's much shorter than that. Very concise, very clearly written, I thought. There's a few amazing things in here. So we already started talking about this last time. We started talking about how this is overall a great design for causal inference with one big exception, namely that there could be other interventions that happened at the same time as the one we're modeling that could explain the effect. And we just don't have a way of controlling for that or excluding those alternative explanations. Okay, not even with, right, what if they introduce the badge and something else that we don't really see or are able to control for? Okay, all at the same time. And whatever change we detect in their dependency freshness is only maybe partly or not at all due to the badge, but really due to this other thing that we're not being able to capture. Right? This is a huge problem, if you're trying to make causal claims. And one that the intervention at different times only partly takes care of by design, right? Because it could still be the case that there's something fundamentally coinciding and associated with the introduction of the badge that co-occurs in all instances, right? The time varying thing from before is useful for some external factors, maybe GitHub changing their policies or who knows what else, but it's not useful for some internal thing that coincides with the intervention by design. So we're still not quite fixing all that. So the question is, how can you do better? And you started talking about this, Owen, already. This is actually really clever here. Right. So this basically here's where this idea of looking at a control group comes from. So again, I told you this earlier. Experiments with random assignment to treatment or control are the gold standard for causal inference. That's great. We don't have experiments. We have observational data over time. But we can approximate, control groups, create appropriate control groups to create this source of counterfactual evidence to compare against the observed treated subjects or whatever they may be. So this is really a powerful idea if you think about it, because now you I guess don't just, well, let's look at this paper. Okay. Now you don't just assume that the counterfactual is the continuation of the linear trend from before the intervention in the treatment group, which is what we did so far. Both of these cases, A and B here, right? What would have happened had there not been intervention is the dotted line. The intervention changed something, there's a change in outcomes, you look at the difference between the two. Okay? This is what we did before, but now we're saying something more powerful. We're saying, instead of assuming that, what if we compare against a control group that is subject to the same confounds as the treated, which is essential, and also did not experience the intervention. Okay, so these are two ingredients that you have to pay attention to. Subject to the same confounds, and obviously did not experience the intervention. That's obvious.
So what is subject to the same confounds?
Right. So let's say we observe some difference in whatever outcome we're measuring here. After the intervention compared to the period before the intervention, we are uncertain if this change is due to the intervention itself or possibly due to or caused by some confounding factors that coincided with the intervention that we're not observing. Confounding factors are usually unobservable factors that could explain the effect, but that are not taken into account by the analysis.
I see.
Right? So, let's say the badge is what we suspect caused this improvement in dependency freshness, but maybe there was something else. They also adopted a tool to automatically update their dependencies at the same time. And the badge does nothing. It's really the tool that causes the effect.
Yeah.
Makes sense?
It's maybe unrelated, but I think it's cool. This looks like comparing groups against one another. But a lot of neuroimaging studies are contrast based because you look at them doing one task, you look at them doing another task, and then you Venn diagram them and look at the differences. So you're not looking at how breathing affects what their brain is doing or something like that. It's probably explained, but I suppose that would be the intra-subject example of subject to the same confounds.
So subject to the same confounds here, I mean, so let's say you're in doubt between the badge and some tool that automatically updates your dependencies, right? And you want to causally attribute the improvement in freshness to the badge and not to the dependency management tool. Okay, so subject to the same confounds means that the control group here that does not have the badge, did not add the badge at that time, must be subject to the same confounds, meaning must have otherwise used the tool you suspect could causally explain the change in freshness. That make sense? You're in doubt between two possible causes, say badge and tool, and you don't know which one caused the effect, right? Could be one or the other. You don't usually observe the tool, which is why this is a problem, otherwise you could control for that, right? You don't actually observe the tool, let's say hypothetically. Right? But the control group should have also used the tool or likely used the tool. Because if the improvement in freshness is due to the tool and not the badge, or partly to the tool, you should see improvements in freshness also in the control group. That was subject to the same confounds, meaning was had introduced the tool or something, or was using the tool. But obviously, you shouldn't see improvements in freshness due to the introduction of the badge in the control group, because by design, they did not introduce the badge. Does that make sense?
Yeah, how deeply would they have to be similar or subject to the same confounds? Like in your example of the sparkles and so forth.
Right.
Would you want the project that you're comparing to have all of the same badges, or do you have a similar structure to the one that you're looking at the time series thing
Yep.
on?
Usually there's two things people do. One is some form of matching that ensures what you described, that they are similar in these other characteristics, except for obviously the big care about intervention. They're similar in these other characteristics, and or along the same lines, there's usually a requirement and test that the trends in the outcome variable you're measuring are parallel between the two groups. Very important. This gives you confidence that they don't have to be identical, although personally I find that a much more convincing design. But the literature does not usually require that. The literature usually requires only that the trends be parallel between control and treated.
So that makes sense to me. Like you would, these are like two indicators that you might want, like A, they're really similar in actuality, like they have a lot of the same badges, they have a lot of the same structure, and also like their trend over time is parallel. Like having these two things together is like sufficient.
Correct. All right. So yes, this is part one. Part two is the theory argument, where you're arguing that they are theoretically comparable. That the samples drawn from the same population or something like that. With this, numerical part of matching and parallel trends and so on, that has to be there. Yes.
So if you were to redo this batch study with this, you would like augment your data set to pair each like repository and that you study with like the doppelganger repository that did the same thing but didn't adopt the badge or whatever.
Correct. And in fact, you could do this a number of times in repeat analysis, or you could do this, for every treated, you could take a random number of, I don't know, you could do one-to-one matching, you could do one-to-n matching. And you use something like propensity score matching to make sure that they are similar in all of these other attributes that you care about.
Sure, you're saying you could just like instead of just having one like control repository, you could have like 100 or something just to make sure that any
For every treated.
Sure, yeah.
For every treated, correct. Matched controls for every treated, at least one.
Yeah, and having more than one control lets you like randomize away any like weird stuff that's happening.
Correct. Yeah.
Yeah.
So this is great and very often done. This is great in our field in general, because usually, at least in the space where I do research, like open source repositories and whatnot, there's so much data available that you can always downsample to arrive at these kinds of appropriate control groups. But there's just enough data to begin with that even after repeated sampling and matching and so on, you're still left with something that's large enough to do statistics over, which is great. Which is why I like working where I'm working. Yeah.
If the control group has a different lines of different scope of lines, can we say that the intervention is not effective?
If the control group has different trends in the outcome variable than the treatment group before the intervention, it probably means it's not an appropriate control group, so you can't really conclude much. I don't know if I would say that the intervention was not effective, as much as I would say that I cannot conclude whether or not the intervention was effective. See what I mean? I'm just like, I don't know. It may have been, it may have not have been. I just don't have enough evidence to be confident. Because the control group is maybe not appropriate. Okay. This is a really powerful idea. Okay, so now how do people do this? Where do you get the controls from? So this paper gives a few good examples. Let me see if I can find them. Maybe in the beginning. Let's see. Yeah, so here's one sentence illustrating the problem. If the vaccine was introduced in a country that is undergoing rapid economic development, there could be a reduction in disease after the vaccine introduction that is just due to economic development period and better nutrition, not due to the vaccine. Okay, control series. Okay, yes, okay. Okay, right. So the control group, you could select to measure the same outcome as the treated, but in an untreated population. So in our case before, you still measure dependency freshness in repositories, but the repositories didn't have the badge. Okay. Or, so I guess here I'm saying mortality in Ireland, outside Dublin, as the control to assess the impact of coal sales ban on mortality in Dublin. Right, so outside Dublin versus inside Dublin is the control here, and the outcome is the same. Or, and this is very interesting, the control might be a different outcome in the same population. Okay. So aspirin-related deaths as the control to assess the impact of paracetamol. And I think, Owen, you had this example maybe in your deck. I think here you talked about the nursing home thing. Wait. Prescribed drugs. Same. This would be the same outcome in different population, right? So we give an example of the first one, not different outcomes. Same outcome, different population. Not different outcome, same population.
Yeah, yeah. Well, because of the interventions of different outcomes.
Let me see if I have some better examples. I think there were a couple in the paper. Let's see. Example one. Let's see. Examples. Yeah, look. Okay, so this is some sort of hospital contracted infections as the outcome. Right, so did you get sick with some bacteria infection from being in the hospital? Or did you get sick with some bacteria infection? And the dark line is for people that were hospitalized, and there was some policy introduced at some point to try to reduce these infections. And the gray line is in the community at large, right? So not people that were necessarily hospitalized. So here the idea is that, you know, maybe just I don't know, the weather or something could have affected the incidence of this infection, right? But if that's the case, it should have affected it in both populations. So really, you know, you can compare the changes in trends and level between the control and treatment to get a much better sense of the causal impact of this policy intervention that was introduced in the hospital here. Okay, make sense?
So here is different populations, same outcome.
Different populations, same outcome. Right. So this would be that. The next one over is the other one. This is diarrhea cases in children younger than 5 on the y-axis. And this feels the same.
I understand, I don't know if I'm understanding it correctly, but my understanding is that this is when the black flags and dots are rotavirus, kids who get diarrhea due to the rotavirus, and gray line is for you get a diarrhea for non-rotavirus caused reasons.
Correct, yes. Right, but it's the same outcome, right? It's incidence of diarrhea.
Yeah.
In different populations, the rotavirus infected ones and the other ones.
Ah, okay, yeah.
So it feels like the same one again.
Yeah.
It feels like same outcome, different populations again.
I'm sorry, what's the issue? So the intervention is that they got vaccinated, right?
Interventions that they got vaccinated. Yes.
Right. So what's the issue?
So I was looking for a good example. I mentioned earlier that there could be 2 kinds of control groups.
Oh, sure.
Right? So I was looking for a good example of the other kind, where you have a different outcome in the same population, as opposed to the same outcome in a different population. Elizabeth?
I have a clarification, so I'm having a bit of trouble understanding I guess the granularity at which things are being done. So with the GitHub repositories, you have like a ton of GitHub repositories, and you're doing this linear analysis on all of them, and then you're normalizing to this intervention was done at this point in
Yep.
time. So were those GitHub repositories, were they all have the intervention done? And
Yes.
so that's okay.
Yeah,
So
no control group.
with those, it works because you're controlling for things within the model, but you don't have a control group, and then this is adding control group because you are doing some type of linear model and then trying to claim something about it that you need a control group for.
This is controlled by design because I have a comparable sample that is similar to the one that was treated, except for the treatment. So this allows me to control for something like adding the tool at the same time, which would have affected both the control and the treated in this design, which I cannot do necessarily with the previous design where everybody gets treated.
So so you don't need a control group in the GitHub repository case because.
I do. It would have been better with a control group. You would have been stronger with a control group.
So it's mainly for establishing concepts.
Yes,
Okay.
which is what you strive to do in the first place in general. Yes. Yes, and having done something like this would have been better in the badges analysis. Yeah. Okay, so now I want to show you 2 things that are important here. So I don't yet have a good example, I don't remember, of the other case of control, but we'll leave that aside for now. How do you actually model something like this? This is quite important, so please pay attention to this part. Let's see. Okay. So two groups, intervention group and control group. And there's some, what is XT? XT is the intervention. XT is a flag that tells you whether the intervention has occurred or not at time t. It's the before whatever thing it has. So obviously the control group does not have the intervention. This did not have the intervention by construction. But it has the all the same other things. What is G? G is combined effect of unobserved confounders. So basically, everything else except the intervention that you have in both cases. And whatever is left over, the error term. Let's see. Equation 6 is a common trend model. Both use here a trend. Blah, blah, blah. Assuming the common trend, we can eliminate the effect of the unobserved confounders by subtracting the control series from the intervention series. This is the billion-dollar idea for today. You take the difference between treated and control in measures of the response variable. So say dependency freshness or number of diarrhea cases or whatever. You take the difference between those two time series at the same time. You're automatically eliminating all of the effects of these unobserved confounding factors, because by design, you expect them to impact the control group as well as the treatment group. Remember, that was a key assumption, right? The control group must be subject to the same confounds as the treatment group. Right? So we don't know what they are, obviously. If we knew, we were able to estimate them and control for them and so on. We don't know what they are. We can't observe and measure them, which is why this is a problem in the first place. But we can assume by design that they would have affected the control group similarly. And therefore, by taking the difference of those two time series, we get rid of them by design, which is awesome. Okay. So this idea of looking at the difference is something that in econometrics people have won, Nobel Prizes or the equivalent for. Basically, super awesome idea for causal inference. So, but it's not easy, right? You still need to find an appropriate control group and believe that it's appropriate and establish parallel trends and whatnot. So it's not like this is, I haven't really solved the problem. I've just shifted the problem somewhere else. Right? But so long as you can find such an appropriate control group, this is an awesome design. Okay. So the regression here, let me actually show you what this would look like. Yeah, this guy. So model 2. What is this? What was this? This was, yes, the bacteria infections in hospitals. Model 2.
Those equations, how do you know that something is in the G function versus an anchor? Like, wouldn't you need to know the split of those in order to still find the difference between the two?
The error is randomly distributed. So I guess you inspect the residuals and see if there's a pattern, and if there doesn't look like there is one, you're happy.
Anyway, both those compounding and errors should affect both populations
Yes,
in the same way because one are random and the other are the same.
yes.
Yeah.
Okay, so the, I don't remember what this role thing is. But basically, model 2 here is what we've seen before, time plus intervention plus their interaction. Something we've seen before, the vanilla thing. Okay. Model 3 is this difference idea, the $1 billion idea for today. Okay, where you compute the difference in outcome variables between the treated and the control at the same time points and regress that. Okay, regress the difference instead of just the actual outcome in treated. But so instead of outcome variable and treated group, you now regress the difference between outcome in treated and outcome in control. That makes sense? $1 billion idea, this, I promise. Very clever. And then everything else is the same. So now this is golden. Like when you do this, you're golden because you've eliminated by design, if you have a good control group, these compounding factors. The last one I didn't show you, or did I show you? No, I didn't show you. That's the only one, right? So we have the vanilla one we looked at already, and we have this one where you're modeling the difference instead. Okay, so the 3 examples I have here, the ones from the paper, are showing you that in these 2 examples, the bacterial infections and whatever else, the estimated coefficients, so the interesting ones are 2 and 3 here. Forget about the first one, yes. The estimated coefficients for the intervention effect are very different, and in fact go in opposite directions. Here, this is relative to 1. One is 2x basically, and the other one is 0.8x times. Okay. So not only are they not close, but they're also in opposite directions. Right, which would suggest here, and in this particular example of the bacterial infection in hospitals, suggests here that the design with a control group is super necessary to get a good causal effect of this intervention. Right, so not only does the design without the control group not give you a similar estimate for the effect of the intervention, but it gives you the opposite direction of the effect of the intervention. Right, so one of them will tell you that there's more infections because of the intervention in the design without a control group. The design with a control group shows you that there are fewer when compared appropriately. So this is golden. It's a great example to show you how wrong you could be when you don't have an appropriate control group and you don't model that explicitly. The other example from the paper, this one with diarrhea, I also have here. And this one actually is also very interesting because all of these coefficient estimates are basically the same. So in the diarrhea example, really, the control group design is arguably overkill because you could have obtained reliable estimates even without it. But you don't know this, right? You don't know this ahead of time, is the point. Okay. So, the paper talks about how, this can go horribly wrong. And, in general, this design with an explicit control group is much more golden, for lack of better words, than the design without. So that's really the key idea. This is what I would like you to remember from today's class, this idea of comparing to an appropriate control group that shares or has parallel trends in the outcome variable before the intervention. This is a really Nobel Prize idea, for real. They won one for this.
Why did you say that the signs were opposite?
Yeah, so
I'm guessing it's because of the difference, but.
it was because of. This was, forget about the sign. Take a look at the absolute value. And this was similar to what you had in the figure you presented. It was a multiplicative factor, not an additive factor. Based on how they model this. So it's basically, 1.98 times, greater than 0.81 times as.
It's not logarithmic, right, okay.
Yeah. It's just because of the way that it's set up the model. That's it for today. Thank you.